Hello, our project is called FERA. It's an implementation of the cross-hole radio imaging method, abbreviated to RIM. Our approach to the project is all-encompassing. We have developed the methodology, the equipment, the software, and organized field work. The method itself is not a novelty. Experiments of this kind were carried out back in the middle of the last century. The first version of the equipment, which laid the foundation for the development of our system, was created at the Leningrad Research Institute Virkrut Geofysica. In 2003, we spun off into an independent commercial company. Our group primarily operates in Canada. In 1997, we won a tender from Falconbridge Company to apply the method to the properties in the Sudbury area and have been doing production work there since 1998. Our clients include the two largest nickel companies in the world, Glencore, formerly Xstrata and Falconbridge, and Vale, formerly CVRD and Inco. 2002 was a milestone in our story. This was the year we took part in the initial exploration of one of the largest deposits of the last decade, Nickel Rim, in the Sudbury area. Our surveys contributed to the determination of the boundaries of the ore body, its thickness and bedding angles, which were then used to select new boreholes and to construct the final model. In 2005, a mine was built to develop this ore body and is still in operation today. We also carried out surveys to search for new promising deposits on the periphery of the mine. Our involvement in the development of Nickel Rim gave us a good publicity. As a result, many mining companies in Canada became interested in our service. A few words about how it works. Two uncased boreholes are required for the survey. Downhole receiver and transmitter units are lowered into the boreholes using winches. Now suppose there is a conductive object between the boreholes. When passing through the object, the radiated energy is partially absorbed. The result is a drop in the receiver signal in the absorbing area. Changing the depth of the transmitter also changes the level and shape of the signal, which gives information about the position, size, and shape of the object. Using the collected data, a tomographic reconstruction of the cross-hole conductivity is built, which clearly shows the search objects. The exploration process using the system can be divided into a number of typical applications. The illustration shows an example of searching for unknown objects. Here, the system identified a conductive zone in the space between the boreholes that had no ore intersection. The drilling was found that the zone corresponded to a copper-nickel deposit. The graph on the right shows the difference between the calculated signal for the host medium, blue, and the collected signal, red. The difference is a consequence of the absorption of energy by the conductive object, the ore body. In this example, during the planned drilling, the borehole intersected two ore intervals. Using FERA, it was found that the mineralized zones corresponding to the intersections are elongated, have parallel dips, different lengths, and pinch out without reaching another borehole. As in the previous case, the graph shows the difference between the calculated signal for the host medium and the collected signal. In this case, there was a known extended ore body located in the contact zone. It was also known that the contact changes its structure at some distance, and it was necessary to find out how the ore body changes in connection with this. According to the results of the work, it was found that the ore body on the right loses its mineralization at a distance of 400 meters from the right borehole and finally pinches out at a distance of 450 meters. Those conclusions were confirmed by the verification boreholes. In addition to the outlining of the ore body, a conductive zone was also located on the left, which at that time didn't correspond to the known geological structures. The verification borehole opened up a crushing zone saturated with saline water. Despite the fact that this result was not of practical value in terms of production, it was taken into account when planning underground tunneling in this area. In addition to defining the outer boundaries of the object, the system in some cases helps to determine its internal structure. The figure shows an example where both boreholes disclose extensive intervals of weak disseminated mineralization. The use of the system made it possible not only to determine the shape, size and boundaries of the zone corresponding to the weak mineralization, but also to identify a local area of massive mineralization within the zone. The graphs show the difference between the calculated values of the amplitude and phase of the host medium signal and the collected signal. The system is used often to confirm that the reserves of deposit are depleted and the further support of the related structures are unreasonable. In this case, there was a mine, the explored resources of which were coming to end, and there was a question about its closure. Drilling around the periphery didn't reveal any industrial significant ore zones. As a last step, the company's management decided to carry out the thorough work to make sure that the decision to close the mine was correct. During the research, several conductive zones were identified. None of them were intersected by existing boreholes. Two of those areas are visible in the image. Based on our work, an extended drilling program was approved, as a result of which the volume of potential reserves of the mine was adjusted. At the moment, the company's management has decided to extend the life of the mine for another 10 years. Since the project was originally created as a commercial enterprise, significant attention was paid to productivity. The possibility of data accumulation during the movement of the receiver made it possible to essentially reduce the reading time. Also, we have developed unique hoisting equipment to increase the speed of data reading. A distinctive feature is the ability to work at several frequencies simultaneously, which increases the reliability of the results without reducing productivity and makes it possible both to identify small low-conductive objects and to get information about the massive zone's structure. FARA is able to work within a wide range of geometric parameters. The distance between the boreholes is up to 1 kilometer, the diameter from 42 millimeters, and depths up to 3 kilometers. The ability to register both amplitude and phase characteristics of a signal provides additional information about the medium and expands the possibilities of the further processing. FARA has a two-stage quality control system for collected data, which ensures maximum reliability of the final result. The practice of two-way measurements is a key component of a quality control system. Upon completion of the one-way reading, the downhole transmitter and receiver units are swapped and the reading is repeated. The result is two independent data sets collected for the same panel but from different sites. Those sets are processed separately, after which two independent tomographic images appear, the correspondence of which indicates the overall reliability of the result. The figure on the left shows the tomographic image for the transmitter on the left, in the center for the transmitter on the right, and finally processing on the full data set. As you can see, the images differ only in minor details, which indicates a high-quality result. The photo demonstrates the receiver operator side. The receiver operator is the leader of measurements. He or she gives commands to the transmitter group, monitors the process in real time, makes decisions about stopping reading, taking a repeated control reading, extracting a downhole unit in order to replace elements, etc. Since measurements are taken at a high speed of movement of the receiver unit, a separate role is assigned to the winch operator. He or she monitors the condition of the cable, regulates the speed of movement, and monitors for possible blocking of the unit in the borehole. Our team has accumulated a wealth of experience working underground in operating mines. We are well acquainted with the principles of organizing underground operations, the specifics of the logistics of mines. We are also well aware of the specifics of safety measures during underground work, which are subject to spatial requirements. Thank you for your attention. We invite you to our booth number 10 in Sararka Hall 1, where we can discuss in more detail the questions of work and application of FARA. Also on our website fara-systems.com you can find more information about our system, examples of application, technical details, photos and much more. Thanks again.